So we are going to discuss the term tensile force. So let us consider a simple situation of a block of mass m suspended by a string. So in examples which we are going to discuss in Newton's laws of motion, whenever we use the term string, we mean it as inextensible string. That means we assume that length of the string does not change during the motion of the body connected to the string. That means when the body is suspended by a string, we discuss different situations. The body may be moving vertically upwards or vertically downwards, and some of the problems may be moving in the horizontal direction. But here, in all the examples we discuss in Newton's laws of motion, we assume that the string is inextensible. That means the string does not elongate by any considerable amount due to the weight of the block suspended from it. So let us consider a block of mass m suspended by a string. So let us consider a block of mass m suspended by a string. Let us consider a block of mass m suspended by a vertical string. So I am going to consider three situations. First situation, the block suspended by the string may be moved vertically upwards. Of course, at present I am not discussing any problem. I am just going to discuss the term tension force. So we consider a block of mass m suspended by string. We consider three situations. Situation 1, the block suspended by the string may be moving vertically upwards. The second situation is the block suspended by the string may be moving vertically downwards. The third situation is the block suspended by the string may be at rest. So let us consider the first case. The block suspended by the string is moving vertically upwards. So we can say that the string pulls the block vertically upwards. So the string exerts a force on the block in the vertical upward direction. So when the string pulls the block vertically upwards, we can say that the string exerts a force on the block in the vertical upward direction. That means the force exerted on block by the string acts vertically upwards. The force exerted on the block by the string acts vertically upward. According to Newton's third law, to every action there will be always an equal and opposite reaction. Here action is the force on block by the string which acts vertically upwards. So the direction of the reaction will be opposite to the action. If action is upwards, reaction will be vertically downwards. Here actually the force exerted on block by the string which acts vertical upwards. Reaction will be the force on string by the block. If action is the force exerted on block by the string, the reaction will be the force on string by the block. Both these forces will have same magnitude. But suppose if you draw a free body diagram for the block, in the free body diagram for the block, we must indicate only the forces which are acting on the block. We should not indicate the forces exerted by the block in the free body diagram. That means in the free body diagram for the block, we must indicate this force on block by the string. Should not indicate the force by block on string. This force exerted on block by the lower end of string, we can call it as tensional force at the lower end of string. The magnitude of the tensional force is usually denoted by capital T. The magnitude of the force exerted on string by the block will be same as the magnitude of force on block by string, because action and reaction force are always same in magnitude. This is T, this is also equal to T in magnitude. But when you draw the free body diagram for the block, the free body diagram for the block, we must show only the forces which act on the block. That means the force exerted on block by the string will be shown in the free body diagram. But the force by block on the string should not be indicated free body diagram for the block. In some exceptional examples, we may draw a free body diagram for the string, separate free body diagram for string. In case you draw a separate free body diagram for the string, this force on string by block should be indicated in the free body diagram for the string. Coming to this case, the block suspended by string is moving vertically downwards. So even in this case, you can say that the block pulls the string vertically downwards. So the block exerts a force on the string in the vertical downward direction. So the force on string by the block acts vertically downwards. Therefore, from Newton's third law, you can say that the force on block by the string acts vertically upwards. This force exerted on block by the lower end of string, we call it a magnitude. This force as tensional force at the lower end of string, denoted by T. That means so whether the block moves vertically upwards or vertical downwards, in both the cases you can observe that what I would like to tell you is that force on block by the string acts upwards. Even in this case, also we can say when the block suspended by the string is at rest, the block pulls the string vertically upwards. So block exerts a force on string in the downward direction. The block pulls the string vertically upwards, so the block exerts the force on string in the downward direction. So force on string by block acts vertically downwards. So from Newton's third law, the force on block by the string acts vertically upwards. So in all the three situations I have shown, that means whether the block suspended by the string is moving vertically upwards or moving vertically downwards or at rest. In all the three cases, the force exerted on block by the lower end of string we call tensional force, acts vertical upwards along the string and directed away from the block. But when you draw the free body diagram for the block, in the free body diagram for the block, we must show only the forces which are acting on the block. We should not indicate the forces by the block. Of course, in each case, action and reaction forces are always same in magnitude. So, T, the magnitude of the force on block by string, magnitude of the force on string by block will also be equal to T. I mean magnitude or modulus will be same for action and reaction forces. But in the free body diagram, we must show only the forces acting on the block. So when you draw the free body diagram for the block, any one of the situations shown in the figure, we show the tension force on block with the string in the free body diagram, which acts upwards. And of course, we have to also show the weight of the block in the free body diagram. Weight of the block is the gravitational force on the block by the earth, tracked vertical downwards. So free body diagram for the block is drawn in the same manner for all the three situations shown in the figure. So to discuss how we evaluate the tensional force at different cross sections of a rope or string, I would like to discuss one problem based on this discussion. So look at the problem on the screen. Problem 7. Consider a block of mass M suspended by a uniform rope of mass m, which is pulled vertically upwards with an acceleration of magnitude a, as shown in the figure. In terms of M, small m, small a and g, what is the magnitude of? I am going to show you three parts in the question. First part of the question, pulling force applied at the upper end of the rope, force on block by lower end of the rope, tension force acting normal to the cross section at the middle of the rope. So here I am going to show you the diagram also. I think you can make out the situation. The block of mass, you can look at the diagram there. You can better copy this diagram on paper or in your notebook. You can observe that the block of mass M is pulled vertically upwards with uniform rope of mass m in the vertical upward direction with an acceleration of magnitude a. There are three parts of the question. The first part of the question, you are asked to find the magnitude of the pulling force applied at the upper end of the rope. In the second part of the question, you are asked to find magnitude of the tensional force on block by the lower end of the rope. Third part of the question, you are asked to find magnitude of the tensional force acting normal to the cross-sectional area at the middle of the rope. So don't just consider it as a problem here. We are not just discussing a problem. We are going to discuss some important conclusions while solving this problem. Therefore, irrespective of whether you may be familiar with the solution of the problem, some of you may be able to do faster, easily, but still I advise you to listen to my explanation, listen to the discussion about the problem, so that you get more general approach for calculation of tensional force in the problems in connecting bodies. So I am going to work out this. So there are To solve the first problem, there are two methods you can follow. One method is you can draw a separate freeboard diagram for block and separate freeboard diagram for the rope. So when we draw a separate freeboard diagram for the block, the forces acting on the block must be shown in the freeboard diagram for the block. The forces acting on the rope should be indicated in the freeboard diagram for the rope. So here, look at the solution. So in this case, the rope pulls the block vertically upwards. The rope exerts a force on the block vertically upwards. So in this case, the rope pulls the block vertically upwards. So we can say that rope exerts a force on the block vertically upward direction. Therefore, the force exerted on the block by the rope acts vertically upwards. The rope pulls the block vertically upwards, so we can say that rope exerts a force on the block in the upward direction. So the force on the block by the rope acts vertically upward. According to Newton's third law, to every action, there will be always an equal and opposite reaction. Here action is the force on block by the lower end of the rope, which acts vertically upwards. So reaction will be in the opposite direction. Here action is the force on block by the lower end of the rope. Reaction will be the force exerted on rope by the block. So the rope pulls the block vertically upwards. We can say that rope exerts a force on the block vertically upwards. According to Newton's law, to every action there will be always an equal and opposite reaction. Here action is the force on the block by the rope, which acts vertically upwards. So direction of the reaction will be vertically downwards. So if action is the force on block by the rope, reaction will be the force on rope by the block. From Newton's third law, action and reaction forces will be same in magnitude. So if capital T represents the modulus or magnitude of the force on block by the lower end of the rope, then the modulus or magnitude of the force on lower end of the rope by the block will also be equal to T. Let F denote the magnitude of the pulling force applied on the upper end of the rope by an external agent. So here I am going to draw a separate free body diagram for the rope and separate free body diagram for the block. I am going to draw separate free body diagram for the rope and separate free body diagram for the block. Of course, it is understood that FBD means short form for free body diagram. The force acting on the block must indicate free body diagram for the block. The force acting on the rope must indicate free body diagram for the rope. So in this action-reaction pair I have shown in the figure, action is the force on block by the rope. So action is the force on block, so it should be indicated in the free body diagram for the block. act vertically upwards. This reaction is the force on rope by the block. So it should be shown in the Tree-Bar diagram for the rope. So the forces which act on the rope must be shown in the Tree-Bar diagram for the rope. The forces which act on the block must be shown in the Tree-Bar diagram for the block. Here actually the force acting on the block, so it should be indicated Tree-Bar diagram for the block. Reaction is the force acting on the rope, so it should be indicated in the Tree-Bar diagram for the rope. So you can observe that this action and reaction forces are shown in different Tree-Bar diagrams. Now this F is the pulling force applied on the top end of the rope by an external hinge, so it can be shown in the Tree-Body diagram for the rope. The force acting on the rope should be shown in the Tree-Body diagram for the rope. Then the another force acting on the rope, which is its weight. The weight of the rope is the gravitational force on rope by the earth, which acts vertically downwards from center of gravity of the rope. Similarly, another force which acts on the block is the gravitational force on the block by the earth, that is the weight of the block. The magnitude of the weight of the block is equal to capital M into small g, which is the gravitational force on the block by the earth, which acts vertically downwards. Here both the block and the rope are moving vertically upward with same acceleration. So let us apply Newton's second law separately for block and Newton's second law separately for rope. So we choose the upward direction as positive direction, downward direction is negative direction. So resultant force on the block in the upward direction is equal to capital T minus mg. According to Newton's second law, resultant force of the block must be equal to product of the mass of the block and its acceleration. Call it as equation 1. Next, look at the Tree-Bar diagram for the rope. The pulling force applied at the top end of the rope acts vertically upwards, the positive direction. The other two forces act vertically downwards, opposite to the direction of the motion. So resultant force on rope in the upward direction can be written as F minus T minus small m into g. According to Newton's second law, resultant of all the forces acting on the rope must be equal to product of its mass and acceleration. So if you add the equations, so T minus capital M into small g plus F minus T plus small m into g equal to capital M into A plus small m into A. So you get capital F minus capital M plus small m into g, you get capital M plus small m into A. You can arrive at this equation directly also when we consider the rope and block together as one system. In some of the numerical problems, we directly consider the rope and the block together as one system. Particularly if you are just asked only to find the magnitude of the pulling force applied at the upper end of the rope. Suppose if you are not asked to find the value of T, if you are just asked to find only the magnitude of pulling force applied at the upper end of the rope. In that case, you can consider block and the rope together as one system. So in general, when two or more number of objects move linearly in the same direction with the same acceleration, you can consider those objects moving together in the same direction with same acceleration as one system. But when we consider the rope and block together as one system, then the force on block by the rope should be treated as the internal force. The force on rope by block should also be considered as the internal force. Internal forces will not enter into the equation of Newton's second law when you apply Newton's second law for system. That means I am discussing the alternate method to arrive at the same equation. Of course, answer will be obtained by just solving the last equation. So from last equation you can write magnitude of the pulling force applied on the rope at the top end of the rope by the external agent is capital M plus small m into G plus A. That is the answer for first part of the question. Let us first finish the first two parts of the question. From first equation, the magnitude of tension force on block by the lower end of the rope can at mg plus ma or m into G plus A. So that is the answer for second part of the question. But here I would like to extend the discussion beyond the solution of the problem. In case if you consider rope and block together as one system, that means I am talking about the alternate method for first part of question. That is alternate method to calculate the pulling force. If you consider rope and block together as one system, then you can draw the free body diagram for system in this way. That means only two forces act on external force act on system. One is the pulling force applied at the upper end of the rope by an external agent. One is the second one is the gravitational force by the earth on the system. That is weight of system is equal to total mass of system into G. The system is moving upwards with acceleration here. That means if you consider block and rope together as one system, or in general if two or more number of objects move together with same acceleration in a straight line path, we can consider those objects which are moving together as one system. Then the force applied by one object in the system, another object in the same system, is called as the internal force. These internal forces should not be shown in the free body diagram for the system. So this T is not shown therefore. So resultant force on system you get F minus, that is the same equation you get. F minus capital M plus small m into G. That is equal to mass of system into acceleration. Then you arrive at the same answer. So in case you want to copy the solution of the problem, you can copy down the solution of the problem. To finish writing the solution of the problem, I would like to work out the third part of the question. The third part of the question, you are asked to find the magnitude of the tensile force which acts normal to the cross-sectional area at the middle of the rope In case you need more time to copy the solution of the problem, you can take a pause and take more time. So coming to third part of the question, the third part of the question, you are asked to find magnitude of tension force acting at the cross section of the middle of the rope. So because it's uniform rope, that means it has same density and same area of cross section throughout the rope. So the upper half of the rope above the cross section of the middle of the rope will have a mass small m by 2. The lower half of the rope below the cross section of the middle of the rope will have mass small m by 2. So this upper half of the rope to exert some force on the lower half of the rope at this cross section. That means the net force exerted by the upper half of the rope of mass small m by 2 on the lower half of mass small m by 2 acts in the upward direction. That we call tension at the middle of the rope. So magnitude of tension acting normal to any particular cross section of the rope will be the force, magnitude of force exerted by part of the rope on one side of the cross section, on the other part of the rope on the other side of the cross section. So I consider the lower half of the rope blocked together as one system of mass capital M plus small m by 2. I consider the lower half of the rope and the block together as one system of mass capital M plus small m by 2. So here the upper half of the rope pulls the lower half vertically upwards with certain force. Let T dash denote the magnitude of this force exerted on the lower half of the rope by the upper half. T dash is the magnitude of the force exerted by the upper half of the rope and lower half of the rope. According to Newton's third law, every action there will be always equal and opposite reaction. Action is the force exerted by the upper half on lower half. So from Newton's third law, the direction of the reaction will be opposite action. If action is upward, reaction will be downwards. If action is the force exerted on the lower half by the upper half, which acts vertically upwards, reaction will be the force on upper half by the lower half, which acts vertically downwards. So here at the cross section, at the middle of the rope, action is the force exerted by the upper half of the rope on the lower half of the rope, which acts vertically upwards. So reaction will be the force exerted by the lower half of the rope on the upper half, which acts vertically downwards. That means this T dash is the force exerted on the lower half of the rope. Action is the force exerted on the lower half of the rope by the upper half of the rope, which acts upwards. This T dash is the force exerted, reaction force, is the force exerted on upper half of the rope by the lower half of the rope. Suppose if you consider the lower half of the rope and the block together as one system, of mass capital M plus small m by 2. Then in the free body diagram for this system, you must show only the forces acting on the system. That means the force, this action, the force exerted on the lower half of the rope by the upper half, must be shown in the free body diagram for this system. But reaction is the force exerted by the lower half of the rope on upper half. That means reaction is the force by the system. So in the free body diagram for system, we must show only the forces acting on the system. We show only the external force acting on system. should not show the forces exerted by the system. So only this action should be shown in the free body diagram. So T dash is the magnitude of the tensile force exerted on the lower half of the rope by the upper half of the rope, which acts vertically upwards. So weight of the system acts vertically downwards. That is a gravitational force exerted on the system by the earth. That means here we are considering the block and the lower half of the rope together are one system of mass capital M plus small m by 2. So this will be the free body diagram for system. The system is moving upward with acceleration A, so we choose the upward direction as positive direction. So magnitude of the resultant force on the system of mass capital M plus small m by 2. Can write T dash minus capital M plus small m by 2 into G. From Newton's second law, the resultant force system of mass capital M plus small m by 2 will be equal to product of mass of the system and acceleration of the system. So you can write therefore from this equation, if you take this term to the right side, that means we have written here resultant force on the system of mass capital M plus small m by 2. So from this you can write T dash equal to capital M plus small m by 2 into G plus capital M plus small m by 2 into A. So magnitude of the tensional force acting normal to the area of cross section at the middle of the rope. Capital M plus small m by 2 into G plus A. So this is the answer for the third part of the question. So with this we have completed the problem. Of course, you can also arrive at the answer by another way. That means if you consider only the upper half of the rope as one system, of course it's not necessary to solve every problem by the alternate method. Only for analysis we are discussing the problem, beginning problem, to have more clarity of calculation of the tensional force. For upper half of the rope of mass small m by 2, if you consider it as one system, then this action and reaction pair shown at the cross section middle of the rope, this action is the force by the upper half of the rope. That means at present I am considering the upper half of the rope as system. That means free body diagram for the upper half of the rope of mass small m by 2. I am going to draw the free body diagram for the upper half of mass small m by 2. So this is the force, this T dash is the force exerted by the upper half of the rope on lower half. That is by the system of mass small m by 2. So it should not be shown in the free body diagram for system. So this reaction force shown in the figure, this T dash is the force exerted on the upper half of mass small m by 2 by the lower half of the rope. So this force acts on system of the mass small m by 2, that is system of the upper half of the rope of mass small m by 2. So this T dash must be shown in the free body diagram for that means if you consider that means I am going to separately apply Newton's second law for the upper half of the rope of mass small m by 2. That means for that we consider the upper half of the rope of mass small m by 2 as one system, as one body of mass small m by 2. So on this mass system or body, the force T dash acts downwards. The pulling force applied at the upper end of the rope acts upwards. The weight of the system acts downward, which is a gravitational force on the system by the earth. So this is a free body diagram for the upper half of the roof of mass small m by 2. That means if you consider upper half of the roof of mass small m by 2 as one system, this will be the free body diagram. So resultant force on this system in the upward direction, in the direction of its motion, the F minus T dash minus m by 2 into g. That means here I am discussing only the alternate method. The problem we have already completed by this step. I am just discussing alternate way you can do it. Because some students may be curious, why not we apply Newton's second law for the upper half of the rope instead of lower half of the rope. So that way you can do this way also. From Newton's second law, resultant force on the system of the rope of mass small m by 2, that is resultant force on the upper half of the rope of mass small m by 2 must be equal to product of mass of the rope, mass of system into acceleration, mass of the upper half of the rope into acceleration. So from this you can find T dash equal to, already we have calculated F in the starting part of the problem. You can substitute F here. You can write F equal to capital M plus small m by into G plus A, which we have calculated in the first part of the question. Now if you substitute this value of F in this equation, you can find T dash. You can do the simplification part yourself. So I have solved this problem mainly to emphasize one conclusion. I have solved this problem to emphasize one conclusion. See here again, let us write all the three answers of this problem at one place. So those who want to copy the solution of the problem, they can copy down the solution of the problem. In case you need more time, you can take a pause and take your time to copy the solution of the problem. So here the problem is completed, but still there is some important discussion we want to do based on the answers of the problem. So we have, again I write the answers. We got magnetic pulling force applied at the upper end of the rope by the external agent who pulls the rope. Is given by F equal to capital M plus small m into G plus A. This is at the upper end of the rope. The magnetic tensional force on block by the lower end of the rope, we calculated, that is capital M into G plus A. That is the answer for second part of the question. This is at lower end of rope. That is magnetic tension force at lower end of the rope is equal to capital M into G plus A. That is magnetic tension at lower end of the rope means it is equal to the magnetic force on block by lower end of rope. Of course, that is same as the magnetic force by the block on the lower end of rope. Action and reaction will have same magnitude. This capital F represents the magnetic pulling force applied at the upper end of the rope, or you can say magnetic tensional force acting at the top end of the rope is capital M plus small m into G plus A. And we have calculated magnetic tensional force acting at the middle of rope. Magnetic tensional force acting normal to the area of cross section at middle of rope. That will be equal to capital M plus small m by 2 into G plus A. So there will be tensional force acting normal to every cross section of the rope. So, but here in this problem, you are specifically given the mass of the rope. But in most of the problems we discuss in connecting bodies, the mass of the rope will be negligible. The mass of the string or rope will be negligible compared to the mass of block. So if the mass of the rope is negligible compared to mass of the block, the mass of the rope is suppose negligible compared to the mass of block, then you can neglect small m in the above equations. So if you neglect small m here in the first equation or put small m equal to 0 in the first equation, then capital M can be written as capital M plus 0 into G plus A. And there will be no change in the value of tension at the lower end of rope. You get the same result even if mass of the rope is neglected. Capital M into G plus A. If you neglect small m in the last equation, you get magnitude of tension T dash, middle of rope, capital M plus 0 by 2 into G plus A. So that means if the mass of the rope is negligible compared to the mass of block, you get T dash to be same as T equal to F. That means if the mass of the rope is negligible compared to the mass of the block, the magnitude of tensional force on block by lower end of rope, same as the magnitude of the pulling force F applied at the upper end of the rope. And magnitude of tensional force acting normal to the cross section at the middle of the rope will also be same as the magnitude of pulling force applied at the upper end of the rope. The same way you can show that magnitude of tensional force acting normal to any cross section will be same as the magnitude of pulling force applied at the upper end of the rope. That means the conclusion is that the mass of the rope is negligible compared to the mass of the block, then magnitude of the tensional force will be same at all cross sections of the rope. So in general, if a block is suspended by a string, then said that the mass of string is negligible compared to the mass of the block, then magnitude of tensional force will be the same at all cross sections of the string. So I will continue my discussion in my next class.